Hello. So for exercise 2.8 of our Introduction to Thermophysics, we're asked, we're said, we have two Einstein solid A and B, each containing 10 oscillators. So we have that, actually I'm going to make a main instruction first. And A is equals to 10, as well as NB. So we can say that N total is equals to 20. And then we know that there's 20 energy units. How many macrostates will there be? Well, the number of macrostates will simply be 20 plus 1, so 21 macrostates. Because we could just say that, object A can have, just say, little n number of energies, while object B will have to have 20 minus little n. So if we assign the A has 0, then B will have 20, then 1, 19, 2, so on, 18, so on. So total number of macrostates is 21. What is the total number of, macrostate is 20. What's the total number of microstate? Well, we have to use the formula. The formula is that NQ is equals to N, or same thing, but the Q plus N minus 1 factorial over Q factorial times N minus 1 factorial is equals to, well, we're going to have then the top, we're going to have, well, actually, let me write it. So of 20 comma 20, it's going to be equals to 20 plus 20 minus 1, which is equals to 39 factorial. Divided by, is that 20 factorial times 20 minus 1 factorial. So we're going to have divided by 20 factorials times 19 factorial, which is equals to 6 times 89 times 10 to the power of 10 microstates in the system. Now, what is the probability of finding all the energy in solid A? Well, let's say that part C, we have that solid A has all the energies. So he has 10 oscillators with 20 energies. Well, this is equals to 10 plus 20 minus 1 over 10 factorial, of course there's a factorial up here, times 20 minus 1 factorial. So here we would have 29 factorial divided by 10 factorial times 19 factorial. And here we have 2003010. This is the number of microstates. Remember that it's not a number of probability, but that's not the probability. So the probability is this number that we just found. So microstate 10, 20 divided by the total. So in this case would be this number that is already pretty big, but it's something even bigger over here. This one right here, which is equals to 6.89 actually. Is equals to 2.91 times 10 to the power of negative 4. This is the probability of finding it. Then we ask, what is the probability of finding exactly half the energy in solid A? Well, as you see, the probability of C is very small, so it's very unlikely to have all the energies in one single object. So, for example, it's impossible to put a cube of ice and a coffee cup next to each other and have the coffee cup to hold all the energy while the ice has no energy. All right. So for D instead, it says what is redefining exactly half the energy in solid A? Well, again, we have to find the number of microstates where half the energy is in A. So we're going to have 10 oscillators for number A and 10 energies because that's half. So we have 10 plus 10 minus 1 factorial divided by 10 factorials times 10 minus 1 factorial, which is equals to 19 factorial divided by 10 factorials times 9 factorials, which is 9, 2, 3, 7, 8. And the probability would be same formula over here, just changed. Oops. One times 34 times the power of negative 6. This seems wrong. Oh, of course, because well, here I didn't have to multiply by anything because we have all the energy in one, for example, because if we, this is for object A, but then we have to find the one for object B, which is equals to, well, in this case we have no energies, but still 10 oscillators, so we have 10 and 0, so we have 10 plus 0 minus 1 factorial divided by 10 factorial and 0 minus 1 factorial. So well, actually I don't even check it. We just know that there's only one microstate for this configuration where we have 10 oscillators and 0 energies. This is equals to 1 oscillator, one thing, because there's 0 energies. And then we have that our total should be A times B, which is equals to, of course, this part right here. So that's correct for the first part. For the second part instead, we're going to have the second one. So this one is A. The second one will then have, again, 10 oscillators and 10 energies. So we'll have the same exact thing. So it will be equals to this. So in order to find the total, we multiply the two. So it would be A times B, which is equals to 90,378 times 10,378, which is equals to big complicated number 85336948884. Okay, it's a pretty ugly number. That's what we get. So again, we're gonna have 85336948884 divided by our total. We get something much bigger, in fact, which is equal to 0.12. This probability to have half and half. And then the last question, which is E. It says, on the work circumstances will this system exhibit irreversible behavior? Well, we know that irreversible behavior happens when we have energy flowing from one from one object to the other without any energy going back. This happens when there's a lot of energy in one object and on the other. So for example, if all the energy stored in our object B, then we can actually write down if all our energy started in object B, then it would flow spontaneously. We have to remember this, spontaneously, to object A, and this would be an irreversible behavior because, of course, there's not going to be all the energy flowing from, there's not going to be then energy flowing from A to B. This would be irreversible behavior as the energy wouldn't all flow back to object B. Now, of course, this also works for the opposite. So if all energy was in object A, it will go to object B, and we just switch A and B pretty much.